Okay, so today what we're going to add to stuff is the fact that oftentimes our reactions involve gaseous things, and we learned last chapter that weighing gases is going to be hard. So grams is not going to be where we want to start. Because how many grams of helium are in a balloon? Oh, that would be hard to find. Because it's floating away from your balance. Okay. And we're really not going to do anything new. We're just going to do what we did with gases last time. We can't measure gases very well by weighing them, but we can measure their volume pretty easily. You just take whatever the container is, stick it to a tub full of water, and however much water comes out, that's how much space the container took, right? So we can also change liters of a gas to moles. In a very specific set of circumstances, in a cold room, another way of saying in a cold room is at STP. And STP was standard temperature and pressure. The temperature was 0 degrees Celsius. The pressure was 1 atmosphere. And we're at about 1 atmosphere right here. We measured it yesterday, and we were at 90.96 atmospheres. So we're pretty close. But we're not at 0 degrees Celsius. That's 0 degrees, that's the temperature ice is at. So temperature ice forms. Okay. But it's easy to make 0 degrees Celsius water. That's why they picked it. All you need is ice floating in your water, and you got 0 degrees Celsius. You don't need a thermometer. As long as you've stirred long enough and the ice is still there, it's going to be 0 degrees Celsius. And if you're at that temperature, then 1 mole is 22.4 liters. And it doesn't matter what the gas is. Okay. So, if 6.45 grams of water are decomposed, how many liters of oxygen will be produced at STP? So on the homework last night, I would have asked you for grams of oxygen. Okay? But today I asked you for liters of oxygen. Okay? And we're going to start it just like last night's work. We start by writing down what they gave us. They gave us 6.45 grams of water. And then let the units tell us what to do. Okay? The unit I want to get rid of is grams of water. And if I want to talk about a different chemical, so I need to go to moles. So I can go from grams of water to moles of water. Oh, so this is the reaction. This is balanced. Make sense? I sped through that step. Sorry. So we've got to take the time to balance that equation. Okay, I set this up so grams of water would cancel out. Now I need to set it up so moles of water will cancel out, so it's got to go on the bottom. And the whole reason for turning into moles is so you can change chemicals. So now I've got moles of water, I want moles of oxygen. And I get those numbers out of the equation. There's a 2 in front of water, there's a 1 in front of oxygen. There's a 2 in front of water, 1 in front of oxygen. And my moles of water cancel out. Now I need to get rid of that moles of water. And instead, last night you would have turned it into grams of water. But instead they asked for volume. So I'm going to turn it into liters. There's grams of oxygen. So I'm turning into liters of oxygen. 4 liters of oxygen. Is 1 mole of oxygen. So I push those buttons on my calculator. 6.45 divided by 18.02. divided by 2 times 22.4 equals, I get what, 4.01 liters. So, hugely different than what you did yesterday. It's the same stuff. Oh, but it changes our diagram, right? The diagram we used yesterday. It changes our diagram because we can use liters, right? I can start with liters and change that to moles, or I can take the moles and change them to liters. But I still have that central of using the equation to change what chemical we're talking about.
So we can basically like change it into atoms.
Well, you mean like that? Because we could also do those too, right? So all this is remember the diagram from last time? It's 2 of them tied together. Over here's the diagram that gets the mole for the first one. Over here's the diagram for mole for the second one. It's that same diagram, just 2 of them hooked together, and the bridge is changing chemicals, the mole to mole step. Okay? So don't spend all your time copying. Here's that diagram for you. And since I had empty space, keep you from flipping back and forth, I put the periodic table on there too. Doesn't take me any more time. Could save you some flipping, right? So there's that diagram. Okay? Whatever they give you, turn into moles. And we have 3 things we can turn into moles: grams, liters, and molecules. Once you get it into moles, change the chemical. And then once you change the chemical, figure out what they want to know about that chemical. Do they want to know liters, grams, or how many pieces there are? That make sense? So let's try a couple. How many liters of CO2 at STP will be produced from the complete combustion of 23.2 grams of CH4, or C4H10? And it said it was complete combustion, so C4H10. That's my fuel. To burn something, I have to have fuel and oxygen. And I always make the same stuff in complete combustion: carbon dioxide and water. I got 4 carbons, so I put a 4. I got 10 hydrogens, so I put a 5 in front of water. That gives me 8 and 5, 13 oxygens. Reactant side, I can't get 13 oxygens because it's odd. So I need a 2 in front of C4H10. Because that gives me 8 carbons, so I put an 8 in front of CO2. Gives me 20 hydrogens, so I put a 10 in front of H2O. And that gives me 16 and 10, 26, 13 O2s. .2 grams of C4H10. Now, and they want liters of CO2. So let's go to our diagram and see how we're going to get there. Okay. So I'm starting with grams, right? So I'm starting here. They want liters over there. So my first conversion factor is going to be to go from grams to moles. And I'm going to get that number from the periodic table. Then I'm going to go from moles to moles. And I'm going to get that number from the equation, those numbers from the equation. And then I'm going to go from moles to liters. And And I get that number is 22.4 liters is 1 mole. That's my plan. So let's carry it out. Okay, so in color, so take that grams they give you and put it on the bottom. That means you want to change it to something else, and if you're talking about chemistry, you want to change it to moles. 1 mole is 4 carbons times 12 is 48.01 or 48.04, and 10 hydrogens is 10.10, so that's 58.14 grams. C4H10, and the grams are gone. Then I want to get rid of moles of C4H10. And the reason I change into moles so I can change chemicals. The chemical I want to talk about is CO2. And in my equation, there's a 2 in front of C4H10 and an 8 in front of CO2. And my moles of C4H10 are gone. So now I want to get rid of moles of CO2. Change it into grams of CO2. Carbon's 12.01 grams. Oxygen 16 times 2 is 32 grams. 12 and 32 is 44.
But why are we changing it to grams of CO2? I thought we...
Yeah, that's not going to give me an answer, is it? This is what we would have done last night. Right? But that doesn't answer the question. They want liters of CO2, don't they? So what am I going to do? Well, I'm just not going to write grams on top. I'm going to write liters of CO2 on top. Right? That's what they want. That's what I should write. So it is just like the ones you did last night. I'm going to put 22.4 up there. Okay, so it is. All we're changing is what 1 mole equals. It's the same math. It's not anything new. So 23.2 divided by 58.14 times 8 divided by 2 times 22.4 equals and I got 35.8 liters of CO2. So I can treat liters just like grams. It's easier. I don't have to add it up. It's always the same number. Okay. What mass of H2O at STP is produced by completely burning 3.6 times 10 to the 12th molecules of CH4? So if you burn 3.6 trillion molecules of CH4, how many grams of H2O would you make? Well, start these problems like I do all of them. Write down what they give me so that I can change the units. Okay. So what unit do I want to get rid of? CH4. Yeah. Seventh. Actually, I need to talk with her about this one. I was supposed to go to the conference, but I didn't make it.
No, just all the time.
So I just had her change the sick leave.
Thank you.
Okay. So you guys are all done with this already while I was gone? Because you know what I want to write at the bottom, right? Molecules of CH4. That's what's got to go there. Now, molecules I can change into moles. And the number is Avogadro's number. 1 mole is 6.02 times 10 to the 23rd molecules. I did all that to change it to moles, so I could change moles of CH4 into moles of what they asked for, H2O. And in my balanced equation, there's a 2 in front of H2O and a 1 in front of CH4. And then change moles of H2O into what they asked me about H2O, and that is grams. So 1 mole, added up already once today, it's 18.02 grams. 2.02 and 16. So I push those buttons. 3.6 EE12 divided by 6.02 EE23 times 2 times 18.02 equals 2.2 times 10 to the negative 10th grams of water. It's not very much water. So 3 trillion molecules of CH4 will make 10 to the negative 10th grams. It's less than a nanogram. Molecules are really small, right? Because you think, well, it's to 10 to the 12th sounds big, but compared to 10 to the 23rd, 23rd's got 11 extra zeros, right? It could be a lot bigger. So that's what the problems are going to look like today. Here they are. The first 3 are just like last night, and then on number 2 they start mixing in molecules and liters.